Welcome guys, my name is IBM and I welcome you to my YouTube channel, Learn Physics with IBM. I am solving Physics 9702 paper 4. This is 4-2, May, June 2022. Without wasting time, I would like to take you to the question paper. So this is May, June 2022. The paper is supposed to be 2 hours. I'll try my level best to keep time. So you can read through the instructions, you can go through the data given, you can read through the formula which is given in this question paper. Me, I will just go straight to the question. Number 1. Define gravitational potential at a point. Remember, gravitational potential, electric potential, this is the work done per unit. For gravitation, it is per unit mass. For electric, it is per unit positive charge. So this is the work done. The work done per unit mass. In moving, the work done per unit mass in moving a test mass from infinity to the point, of course, to the point in the gravitational field, or to the point. So that is what we mean by gravitational potential at a point, the work done per unit mass in moving a test mass from infinity to the point. Starting from the equation of gravitational potential due to a point mass, of course, gravitational potential phi is equal to negative G capital M over R. Due to a point mass, show that the gravitational potential energy of a point mass m of distance at a distance r from another point mass capital M is given by that expression here. So we know that gravitational potential energy is equal to the mass times the gravitational potential. So I'll just combine these two, mass times negative capital G capital M over R, so which gives me negative capital G M small m over R, as simple as that. The figure shows the path of a comet of mass 2.2 times 10 to the power 14 kilograms as it passes around a star of mass 1.99 times 10 to the power 30 kilograms. A point mass x and a point x, at point x, the comet is 8.44 times 10 to the power 11 meters from the center of the star, and it's moving at a speed of 34.1 kilometers per second. At point y, where is point y? Okay, point y is very close. At point y, the comet passes its point of closest approach to the star. At this point, the comet is at a distance of 6.38 times 10 to the power 10 meters from the center of the star. Both the comet and the star can be considered as point masses. So if they are considered to be point masses, then the equation we have just derived can be applied. Calculate the magnitude of the change in the gravitational potential energy of the comet as it moves from position X to position Y. So I will say the potential energy at X, I'll call it EPX, is going to be negative capital G, capital M, small m, over distance for X. And I will say the potential energy at Y is going to be negative G, M over R, Y. Where is the potential greatest? Potential is greatest far away from the star. So the potential is greatest at X. So I will say potential at X, potential energy at X minus potential energy at Y. So the difference or the change in potential energy delta EP is going to be negative G mm over Rx minus negative capital G mm over R at point Y. So which is simply the same as GMM into brackets So this becomes a positive. So it becomes 1 over r at point y minus r1 over r at point x. So I'll just make a substitution. So this is going to be g, which is 6.67 times 10 to the power of minus 11 times small m. Or capital M is 1 point. What is the mass of the star? 1.99, and the mass of the comet is 2.20. So this is 1.99 times 10 to the power of 30. Then the small mass is 2.20 times 10 to the power of 14. Then into brackets 1 over distance from y to the star. Y is 6.38, then x is 8.44 times 10 to the power 11. So this is 6.38 times 10 to the power of 10 minus 1 over 8.44 times 10 to the power of 11. Okay, so I'm just going to check my calculator. I'll start with a bracket. I can start with a bracket, so I'll say 1 divided by 6.38 exponent 10 minus, open another bracket, 1 divided by 8.44 exponent 11. Then I'll multiply backwards times 2.2 exponent 14. Then times 1.99 exponent 30. Then times 6.67 exponent minus 11. So this is 4.23 times 10 to the power of 23. So 4.23 times 10 to the power of 23. So that is the change in gravitational potential energy. State with the reason whether the change in gravitational potential energy in B is an increase or decrease. Remember, the force is attractive. The force is attractive. So moving from X to Y, Y is closer to the star, so it means it is going to be a decrease because the gravitational force is attractive. When I go closer to a mass, then it is going to be a decrease. So I'll say gravitational force is attractive. So moving closer to the mass, moving closer to the star means a decrease in gravitational potential energy since it is maximum at infinity. So I'll say gravitational gravitational force is attractive. The gravitational force is attractive. So moving closer to the star means a decrease. It means a decrease in gravitational potential energy. So it means a decrease in gravitational potential energy because or since it is maximum at infinity. It is maximum at infinity. Okay. Alternatively, you would explain it in terms of work done. If you move closer to another mass, the gravitational force does work. And because it is the gravitational force which does work, it means energy is being removed from the mass. So moving towards means the force does work, which reduces the gravitational potential energy. moving away would mean work is done against the force, which would increase gravitational potential energy. So I would simply say here, the force does work. And so this is a what? So this is going to be a decrease. Next time they will tell you, next time the question will be when the gravitational potential energy increases, or when the mass moves away from the star. And or when the comet moves away from the star. If the comet moves away from the star, it will be moving away, which would mean work is done against the force. And remember, the force is attractive. So if work is done against the attractive force, it means the work done is going to be positive. The work done is going to be causing an increase in gravitational potential energy because it is maximum at infinity. And remember, at infinity, it is 0. Use your answer in B Roman 1 to determine the speed in kilometers per second of the comet at point Y. So let's assume that the change in potential energy is going to be equal to the gain in kinetic energy at point Y. And remember, kinetic energy is a half m. Where there is v, I'll have um, v at y, because at y it is maximum, v at y squared minus v at x squared. So the change in potential energy, we got it as 4.23 times 10 to the power of 23. This will be equal to a half times the small mass, which is 2.2, times 10 to the power of 14. Then the velocity at y, which I'm calling vy squared, minus the velocity at x, which was 34 kilometers per second, 34.1. So this is going to be 34100 squared. Okay, so I'll make vy the subject. So I say 4.23 exponent 23 times 2 divided by 2.2 exponent 14. Then I will say plus 34100, but this is squared. I'm making vy squared the subject. Then I'll find the square root of the answer, and this is giving me 70. So vy is equal to 70769. 70769, or approximately you can say 70.7800. These are meters per second, but we want the answer in kilometers per second, so I'll have to divide this by 1,000. And by 1,000, this is going to be 70.8 kilometers per second. So this is 70.8. A second comet passes point X with the same speed as the comet in B and traveling in the same direction. The comet is gradually losing mass, so the mass is decreasing. The mass of the comet when it passes point X is the same as the mass of the comet in B. Suggest with a reason how the path of the second comet compares with the path shown in the figure. So we have seen that the change in potential energy is equal to a half, or it is equal to the gain in kinetic energy. Note that in both equations for potential energy we had G, capital M, small m, into 1 over r at y minus 1 over r at x. Then for kinetic energy we have a half m into vy squared minus vx squared. So you notice that the mass, if the mass reduces, remember the mass at x is the same for both. So if the mass starts reducing, it will reduce it reduces the gravitational potential energy as it reduces for the kinetic energy. So both expressions have mass which is changing, so it means it can even be cancelled out. In other words, it ends up not depending on the mass of the comet. So I could simply say, since both potential energy and kinetic energy equations, the path is going to remain the same because m can cancel both sides. So I'll say both, since both potential energy and kinetic energy equations include the mass or include small m or include the mass of the comet. The path is unchanged. So the path is going to remain the same whether the mass of the comet is reduced. Okay, so the path is unchanged. So the path remains the same, in other words. Then question number 2 is electric fields, state Coulomb's law. We know that force is equal to a constant times the product of the charges divided by the square of the separation. So this law only applies to point charges. So I will simply say that the force between 2 point charges is directly proportional to the product of the charges and inversely proportional to the square of their separation. Okay, so that is Coulomb's law. The force between 2 point charges is always between 2 point charges. Those are charges whose separation is much bigger than the size of n of the charge. So positronium is a system in which an electron and a positron orbit with the same period around their common center of mass as shown in the figure. The radius r of the orbit of both particles is 1.5 times 10 to the power of minus 10 meters. Explain why the electric force between the electron and the positron causes the path of the moving particles to be circular. So the electric force, of course, if this is a particle moving, its path is that one, and the electric force is going to be between the two particles, which is going to be perpendicular to the path of the particle. This is the force, and this is the direction of the velocity or the direction of the particle. Or I reverse this, it is supposed to be pointing downwards. No, it is in the correct direction because it is clockwise, so it is in that direction. So you notice that the electric force is always perpendicular to the velocity, therefore it is going to provide a centripetal acceleration. As long as the force is directly proportional, as long as the force is perpendicular to the velocity, then the force simply provides centripetal acceleration or centripetal force. So I would say the electric force is constant because remember it depends on the product of the charges and their separation. The product of charges is a constant and their separation is remaining constant. So we shall say electric force is constant and perpendicular to the direction of motion or to the velocity of the particles. Because it is constant and perpendicular to the velocity of particles, so the electric force does not change the speed. So electric force does not change the speed of the particles, but instead provides or causes centripetal acceleration. So it is simply going to cause centripetal acceleration or motion towards the center of the circle, because the electric force itself is constant and is always perpendicular to the velocity. So it can't speed up the particle, but simply it will cause centripetal acceleration. That is, it will cause the acceleration to move. It can't change the speed of the particle. It will simply cause the particle to move in a circle or to provide centripetal acceleration, as simple as that. Show that the magnitude of the electric force between the electron and the positron is given by this magnitude. So we know by Coulomb's law the force F is equal to the product of the charges, which I will just say E squared divided by 4 pi epsilon naught times x squared, where x is the separation between the charges. So I'll substitute. The charges are positron and electron, so the charge is 1.60 times 10 to the power of minus 19, and this should be squared. Divide this by 4 pi. Epsilon is 8.85 times 10 to the power of minus 12. Then times the separation, which is going to be the diameter. The radius is 1.5, so I'll multiply this by 2. So this will be 2 times 1.59 times 10 to the power of minus 10. And this is going to be squared. So I'll start with the denominator because it is more complex. 2 times 1.59 exponent minus 10. I'll square this. I'll multiply by 4 pi times 8.85 exponent minus 12. Then I'll get the numerator, which is 1.6 exponent minus 19, but is squared, and I divide by the answer. So this is giving me 2.276 times 10 to the power of minus 9, or it is approximately 2.28 times 10 to the power of minus 9 newtons. Okay. Then use the information in B Roman 2 to determine the period of the circular orbit of the two particles. So we have already said the centripetal force, the force to the electric field, or the electric force is providing the centripetal force. But we know that the centripetal force is given by mv squared divided by r. And of course, we know that v is omega times r, where omega is 2 pi divided by t. So I will multiply this by r. I have remembered to square it. So if I square, so I have that F is equal to m. Where there is v squared, I will put 4 pi squared r squared over t squared. So I want to find the period, which is capital T. So I have to make 1 r as cancelled out with the square. I have to make t the subject. So t is going to be equal to 4 pi squared r, then divide by, so there's an m somewhere, divide by f, and this is going to be under the square root. So I'll just substitute square root of 4 pi squared times r. R was the radius, which is 1.59 times 10 to the power of, I think it was 11. No, it was minus 10. Minus 10, then times the mass. What was it? Is an electron, so the mass is 9.11 times 10 to the power of minus 31. Then divide this by the force we got as 2.28 times 10 to the power of, was it minus 9? Okay. times 10 to the power of minus 9. So I have to check my calculator. So I'll say 4 pi squared times 1.59 exponent minus 10, then times 9.11 exponent minus 31 divided by 2.28 exponent minus 9. Then I find the square root of the answer. So this is 1.58 times 10 to the power of minus 15. So t is 1.58 times 10 to the power of minus 15 seconds. So 1.58 times 10 to the power of minus 15 seconds. So that is going to be the period. Okay, then positronium is highly unstable, and after a very short period of time, it becomes gamma radiation. Describe how gamma radiation is formed from the two particles of positronium. So we have an electron and a positron. So there will be annihilation when an electron meets a positron. The electron is minus, negative, it meets a positron which is positive. Their mass is converted into energy. That's what we call the annihilation process in medical physics under the PET scan. So I'll say positronium interacts with an electron. The positron interacts with the electron, and the positron, of course, we know the positron is the antiparticle of the electron, and the positron is the antiparticle of the electron. So the positron is interacting with the electron, but the positron is the antiparticle of the electron. So pair annihilation occurs. Pair annihilation. Annihilation occurs. Pair annihilation occurs, and the mass of the electron and the positron, the mass of the electron and positron is converted into energy in the form of gamma photons, and the mass of electron and the positron is converted into energy in form of, or is converted into energy of gamma photons. Okay, so that is how gamma photons are formed. The positron is interacting with the electron, but remember the positron is the antiparticle for the electron. So this pair annihilation, pair annihilation occurs, and the mass of the electron and positron is converted into energy. So state one medical application of the process. So this is the PET scan, the positron emission tomography, or PET scanning. Okay. Question 3, define specific latent heat of vaporization. So vaporization, that is from liquid to vapor. It is specific, that is 1 kilogram. It is latent, that is constant temperature. And then it is vaporization, that is liquid to vapor. So when we talk about specific, we must refer to a unit mass. So I will say the thermal energy per unit mass. Thermal energy per unit mass, that is 1 kilogram required, Or by the way, it can also be vapor back to liquid. So I'll just say change of state from liquid to vapor, or change of state between liquid and vapor, or liquid to gas at a constant temperature. So thermal energy per unit mass required to change state between liquid and gas at constant temperature. So thermal energy per unit mass required to change state between liquid and gas at constant temperature. So that is what we call a latent, specific latent of vaporization. If it is specific latent heat of fusion, it will be thermal energy per unit mass required to change the state between, because it's fusion, fusion will be solid between solid and liquid, but still at constant temperature, because latent means there is no change in temperature. Then the specific latent heat of vaporization of water at atmospheric pressure is 1.0 times 10 to the power 5 pascals is 2.3 times 10 to the power 6 joules per kilogram. A mass of 0.37 kilograms of liquid water at 100 degrees Celsius is provided with the thermal energy needed to vaporize all of the water at a constant pressure. Calculate the thermal energy Q supplied to the water. So of course we know that Q is equal to mass times the latent heat of vaporization. The mass is 0.37. Then the latent heat of vaporization is 2.3 times 10 to the power of 6. From my calculator, 0.37 times 2.3 exponent 6. So this is 8.51 times 10 to the power of 5. 8.51 times 10 to the power of 5 joules. Then the mass of 1 mole of water is 18 grams. So this is the molar mass. I'll call it capital M subscript R, that is the molar mass. And they had already given us the mass small m of water. Assume that water vapor can be considered to behave as an ideal gas. Show that the volume of water vapor produced is 0.68. So we know that for an ideal gas, PV is equal to nRT. But I want you to note that the number of moles is equal to the mass divided by the molar mass. So it means if I make V the subject, it means V, which is equal to nRT divided by P, is going to be the same as small m RT divided by capital M, that is molar mass, then times the pressure. So I'll make a substitution. This is in grams, the other one was in kilograms. So I have to ensure that the unit is the same. So the other one was 0.37 kilograms times R is 8. The molar gas constant is 8.31. The temperature was 100 degrees Celsius, so I have to add plus 273. So it becomes 373. Then I divide by 18 grams to be 18 times 10 to the power of minus 3. Then times the pressure. The pressure is 1.0 times 10 to the power of 5. 1.0 times 10 to the power of 5 pascals. So I'll press my calculator. 0.37 times 8.31 times 373 divided by 18 exponent minus 3 divided by 1 exponent 5. So I'm getting 0.3637. This is 0.637 or approximately 0.64 meters cubed as required. Assume that the initial volume of the liquid is negligible compared with the volume of the water vapor produced. This is a very important statement. The initial volume of the liquid is much smaller than the volume of the water vapor produced. Determine the magnitude of the work done by the water in expanding against the atmospheric pressure. So we also know that work done is equal to pressure times difference in volume. So the pressure was, remember, 1.0 times 10 to the power of 5 pascals. Then the change in volume, they say the initial volume is negligible. So it means the change in volume is just going to be approximately 0.64. So I'll just say times 0.64. Because the initial volume was negligible compared to the change in volume of the water vapor. So that means the change in volume is approximately the same as the volume of the water vapor produced. So I'll simply say 1 exponent 5 times 0.64. So that is 64,000. So this is 64,000. We can write 6.4 times 10 to the power of 4 joules. That's the work done. Use your answer in B Roman 1 and B Roman 3 to determine the increase in internal energy of the water when it vaporizes at 100 degrees Celsius. So we want an increase in internal energy. Okay, so number one, we have to check the sign conventions. So first of all, the work done is going to be negative because there was an increase in volume. So the work done is going to be negative. So I will say work done equals to negative. It is going to be negative 6.4 times 10 to the power of 4 joules. Why is it negative? It's because work is done against atmosphere. Work done against the atmosphere. Work is done against the atmosphere. So the work done on the water is negative. So the work done on the water is negative because there was an expansion. It is the water which is doing work to the surroundings. So the work done on the water itself is going to be negative. So it will be negative 6.4 times 10 to the power of 4 joules. Then the increase in internal energy. Increase in internal energy is equal to, of course, Q plus W. So let's check Q. How much thermal energy is that? So Q was 8.51 times 10 to the power 5, and this was supplied, so it is positive. So this is 8.51. Where am I writing? So this is 8.51 times 10 to the power 5 plus negative 6.4 times 10 to the power of 4. I've just pressed my calculator. That one plus, okay, that is a negative. I'll just say 8.51 exponent 5 minus 64000 to 64,000. So this is 7.87 times 10 to the power of 35. That is 10 to the power of 5. So here I'll write 7.87 or 7.9 times 10 to the power of 5. So that will be the increase in internal energy. Note that I took a negative work done because the vapor, as the water changes to vapor, there is an increase in volume. An increase in volume means a negative work done by the water. A negative work done on the water, because it is the water which actually does work to the surrounding as the expands. Use the first law of thermodynamics to suggest with a reason how the specific latent heat of vaporization of water at a pressure greater than this atmospheric pressure compares with its value at atmospheric pressure. Okay, so first of all, the specific capacity is going to depend on the work done, because remember from the first law of thermodynamics, change in internal energy is equal to Q plus W, and this is ML plus, which is going to be, of course, this will be negative because there's an expansion, so plus minus W or plus negative W. That is the change in internal energy. So it means the latent heat of specific latent heat of vaporization L is the increase in internal energy plus the work done divided by the mass. So if we say the change in internal energy is going to be constant because the final temperature is constant during vaporization, then and the mass, let's say the same water vaporizes, so it is only W which is going to affect. So W is equal to pressure times change in volume. So they are saying use the first law of thermodynamics to suggest with a reason how the specific latent heat of vaporization of water at a pressure greater. So the pressure is greater, the water is at a greater pressure, so that means the work done is going to be more. So if that work done is greater, it means the increase internal the latent heat of vaporization is also going to be greater because the whole of this quantity here would be greater. So we shall say more work is done at a greater pressure. More work is done at a greater pressure. So the specific latent heat of vaporization the specific latent heat of vaporization will be greater. Okay, because more work is done because of the increase, the greater pressure, it means the specific latent heat of vaporization will also be greater. More work will be, or more heat will be required to actually push against the atmosphere to cause a bigger change, or to overcome a bigger change, or to compensate for the bigger pressure difference. Instead, what is meant by resonance? Of course, resonance, when we say an object is, or there is a resonance if the driving frequency is equal to the natural frequency, and the object will vibrate with the maximum amplitude since it absorbs maximum energy. So resonance can be defined as oscillation of an object at maximum displacement or maximum amplitude. Oscillation of an object at maximum amplitude when the driving frequency equals the natural frequency of the object. Okay, so that's what we call resonance. The figure shows a heavy pendulum and a light pendulum, both suspended from the same piece of string. This string is secured at each end to fixed points, as shown in that diagram. Both pendulums have the same natural frequency, F naught. The heavy pendulum is set oscillating perpendicular to the plane of the diagram. As it oscillates, it causes the light pendulum to oscillate. This is Barton's pendulums. The figure shows the variation with time t of the displacements of the two pendulums for 3 oscillations. And we see that the displacements are remaining constant for the 3 oscillations. The variation with the t of the displacement x of the light pendulum is given by this equation. So x equals to x naught sine omega t. That is the general equation. These are x is in centimeters, t is in seconds. Capture the period t of the oscillation. So when I compare the two equations, it means omega is going to be 5.0 pi. That is omega. But remember, omega is 2 pi divided by t. Or you can say t is equal to 2 pi divided by omega, which is the same as 2 pi divided by 5.0 pi. So I just say 2 divided by 5 because pi cancels, that is 0.4. So the answer here is going to be 0.4 seconds. On the figure, label both of the axes with the correct scales. Use the space below for any additional working that you need. So we already know that period is 0.40. Period is 0.40. So period is the time for one complete what? Oscillation. So this is going to be 0.4. This is going to be 0.8. Those are two cycles. And this will be 0, or it will be 1.2. I'm just going on adding 0.4. So this will be 1.2. So here I'll put as 1.0. Here I'll put, this is going to be 0.6. And here I'll put 0.2. So 0.2, 0.4, 0.6, 0.8, 1.0, and 1.2. Then the amplitude was 0.25. So the amplitude is 0.25. So this is 0.25 centimeters, because I said the amplitude x is in centimeters. So it means when I go on adding 0.25, those are 5 small square. This will be 0.50, 0.75, and this will be 1.0. At the bottom, I'll have, after 5 small squares, this is negative 0.25, negative 0.50, negative 0.75, and negative 1.0. Okay, so that is the scale as required. So remember, the amplitude was 0.25 meters, and I've used the amplitude to tell the scale on the vertical. Then determine the magnitude of the phase difference phi between the oscillations of the light and heavy pendulums. Give a unit with your answer. So we know that phase difference is equal to 2 pi. If I want it in radians, I will say 2 pi into the time out of step divided by the period, because I've given us time. What is the time between the two corresponding points? I just look for two corresponding points. Let me check the color. I'm going to look for two corresponding points. For instance, I'll take this point here and this one here. These are corresponding points. So this is going to be delta t. 1, 2, 3, 4, 5. 5 small squares. So that is going to be 0.1. So the time out of step is 0.1. Those are 5 small squares. So 0.1. So this is 2 pi into 0.1 divided by the period, which is 0.4. So a quarter of that, this is going to be, I think this is a half of pi. This is a half of pi in radians. So you can say 0.5 pi in radians. So 0.5 pi in radians. Or you can write a half pi in radians. Or I will press the calculator and I say, okay, 2 pi times 0.1 divided by 0.4. It can be 1.6 radians. If I want to use the angles, I would say phi is equal to 360 into 0.1 over 0.4. So this is 360 times a quarter, which is 90 degrees. So I can say pi is 90 degrees. 90 degrees. 90 degrees. So I either rate 0.5 pi or half pi radians, 1.6 radians, or rate 90 degrees. Define the capacitance of a parallel plate capacitor. Of course, we know that capacitance C is equal to V over Q. No, it is Q over V. So it's the ratio of the charge on one of the capacitor plates to the PD across the plates. It is the ratio of the charge on one of the capacitor plates or one of the plates to the PD. Of course, writing PD is acceptable. Potential difference across the plates. That is capacitance of a parallel plate capacitor. Then two capacitors of capacitances C1 and C2 are connected in parallel. They're in parallel to a power supply of EMF E as shown in the figure. Show that the combined capacitance C total of the two capacitors given by C total is C1 plus C2. Now, if this is the battery, let's say total charge leaving the battery is Q. Of course, when charge reaches here, it splits into Q1 and Q2. So by Kirchhoff's first law, conservation of charge, note that the PD across the capacitors is the same. So I'll say the PD, because they said explain your reasoning. So I'll say PD across both plates, both capacitors is the same. PD across both capacitor plates is the same and is equal to, it is equal to E. It is equal to the EMF of the battery. And then total charge Q total is equal to Q1 plus Q2. Let me call this one Q total. Okay? So total capacitance is equal to Q1 plus Q2. And of course, we also know that charge is equal to C times V. So C total times E, of course, V is E. V is the same as E. It's going to be equal to C1 times E plus C2 times E. Hence, when of course you divide both sides by E, C total is equal to C1 plus C2. As simple as that. Of course, the most important point is stating that the PD across the capacitor is the same, and then showing that total charge is equal to charge at which goes to each of the capacitor plates. Then you show this equation, you get the 3 marks. Then two capacitors of capacitance 22 microfarads and 47 microfarads and a resistor of resistance 2.7 mega ohms are connected into the circuit of the figure shown. Okay, so that is the figure 5.2. The battery has EMF 12 volts. Show that the combined capacitance of the two capacitors is 15 microfarads. So these are capacitors in parallel. For capacitors in parallel, total capacitance is got from the reciprocals. So I'll say 1 over C total is 1 over 22 plus 1 over 47, which means C total is going to be the product, which is 22 times 47 over the sum, which is 22 plus 47. So I'll just press my calculator. 22 times 47 divide by 22 plus 47. So this is 14. This is approximately 15. So this is approximately 15 microfarad. Why isn't it exactly 15? Let me check it again. 22 times 47 divide by 22 times 47. 22 times 47 divide by 22 plus 47. Yeah, it is approximately 15 microfarads. The two-way switch S is initially at position X so that the capacitors are fully charged. Use the information in C Roman 1 to calculate the total energy stored in the two capacitors. Total energy. This is total energy stored in the two capacitors. So we know that total energy is going to be a half total capacitance times V squared. After all, V is the same for both. So this is going to be a half times total capacitance, which is 15 microfarads. That is 15 times 10 to the power of minus 6. Then times the PD across the capacitors, which is 12 volts squared. So 0.5 times 15 exponent minus 6, then times 12 squared. So this is 1.08 times 10 to the power of minus 3. 1.08 times 10 to the power of minus 3. Okay, so that is the total energy. The two-way switch is now moved to position Y. When we move it to position Y, it is now going to be discharging across the capacitors. Determine the time taken for the PD across the 22 microfarad capacitor to become 6.0 volts. Okay, so if I'm considering 6.0 volts, I want you to recall that if capacitors are in series, the charge is going to be the same. So the charge here, the charge Q is the same, and the charge here will be C1 times V1. The charge here will be C2 times V2. But the charge is the same, so it means C1 times V1 should be the same as C2 times V2. They should be the same. Which means if I want to find, for example, V1, if I want to find V1, I'll get C1 over C2 times V2. So V1 is going to be C2 over C1 times V2. Alternatively, I can find, remember V1 or V total is going to be V1 plus V2. In other words, V is divided in the ratio of the capacitances, which means if I want to find V1, I can also say V1 is equal to the total capacitance, which is going to be C total over C1 times the voltage supply V. After all, total charge Q is equal to C1 times V1. And total charge can also be total capacitance times the PD across all the capacitors, total PD. So what I'm going to just do is say total capacitance times PD, which is total charge, is equal to C1 times V1 to find V1, which will be C total over C1 times the voltage, the PD, total PD across both of them. Okay, so I need the initial PD, so I'll need the initial PD. I'll call this one V0 across the 22 microfarad capacitor. And I've said it is going to be total capacitance, which is going to be, so PdV1 is going to be total capacitance over C1 times the voltage supply, which was 12. So this is going to be, was it 15 divided by 22 times when the capacitors are fully charged, the voltage supply is 12 volts. That is a PD across both of them, which gives us 15 divided by 22 times 12. So this is 8.2. Okay, so that is going to be the initial PD across the 22 microfarad capacitor, which means the PD across the other one is going to be 12 minus 22. Okay, so if that is the initial PD, so I'll use the discharge equation. V is equal to V naught e power minus T divided by the time constant R times C. So V is 6.0, but the initial was 8.2. E power minus, we are finding the time, so that is T over R, where R is the resistance, which was 2.7 times 10 to the power of 6, then times the capacitance. Of course, this is total capacitance, which is 15 times 10 to the power of minus 6. So I'm trying to find T. I'm going to introduce ln here. So I'll say ln of 6.0 divided by 8.2 is equal to the power, which is negative T divided by 2.7 times 10 to the power of 6, then times 15 times 10 to the power of minus 6. Of course, the 6 and minus 6, this has cancelled with that. So I'm just going to press my calculator. Ln of 6 divided by 8.2. Okay, then I will multiply this by negative 2. I'll open the bracket, 2.7 times 15. So this is giving me T as 12.65. So T is 12.65 seconds. 12.65 seconds, or I could write 13 seconds. So another alternative, instead of using that method, I would find the PD across both capacitors. So initial PD is going to be, what was the initial PD? Initial PD V naught. This is method 2. And I think method 2 is the easiest, method 2. V naught is going to be the initial PD across both capacitors, which is of course going to be 12 volts. That is across both. Then V is the PD across both capacitors after discharge. So the final PD after discharge is going to be, of course, since they gave us the PD across 22 microfarad capacitor to be 6. Let's find the total PD. Using this expression here, I make V the subject, so V is going to be C1 over C total times V1. If I use this expression here, so it means this is going to be C1, which is 22, C total, which is 15, times 6. I'm trying to find the final PD across the capacitors, both of them. So 22 divided by 6, remember, was across one capacitor. So 22 divided by 15 times 6, that is 8.8. So I repeat with the same formula. So I'll say V, which is 8.8, should be equal to V naught, which is 8.2. No, it is 12, which is 12 volts, times E power minus T divided by R, which is 2.7 times 10 to the power of 6, times C, which is 15 times 10 to the power of minus 6. And I'm very certain this would give you the same answer. You can check the second method and see if it takes you to the same answer. Question 6 is, I think, magnetic fields. State the two conditions that must be satisfied for a copper wire placed in a magnetic field to experience a magnetic force. Remember, force is equal to BIL, and B must be at an angle. If it's not at an angle, then F is going to be B cos theta times I times L. There must be a current, and the angle should not be 0. Because if it is 0, okay, let me use sine. The angle between the current and the magnetic field should not be the angle between the field and the current should not be 0 if I use sine, because if it is 0, then it means there will be no magnetic force. So, number one, there must be a current. There must be a current flowing in the wire. Number two, the angle between the wire and the magnetic field must not be 0. The angle between the wire and the magnetic field must not be 0. Of course, if the angle is 0, it means the current is part of the magnetic field, then Fleming's left hand rule cannot work in that condition. So those are the two conditions for there to be a force. A long air-cored solenoid is connected to a power supply so that the solenoid creates a magnetic field. The figure shows a cross-section through the middle of the solenoid. The direction of the magnetic field at point W is indicated by the arrow. 3 other points are labeled X, Y, and Z. On the figure, draw arrows to indicate the direction of the magnetic field at each of the points X, Y, and Z. Of course, for X is inside the solenoid, and the magnetic field inside the solenoid is almost uniform. Since W is pointing to the right, even at X it will point to the right and to be a parallel line. Then of course at Z it is outside, so it would be like this. It is going like that. So at Z is going to be a horizontal line pointing to the right hand side. And of course at Y it is going to be a tangent. It is going to be at an angle. If I do a tangent to this, it is approximately at an angle of 45 degrees in this direction. Okay, because if I was to draw a continuous loop here for the magnetic field, changing the color, I would draw something like this. Something like that. So it's like this is in that direction, that is in that direction. Here it is a tangent. So that's why I'm saying at Z, at X it is horizontal to the left. At Z it is horizontal to the right. At Y it is a tangent at almost an angle of 45 degrees. I don't know whether this is 45, but at least it's approximately 45 degrees. So that will be the diagram we are looking for here. Okay. Then compare the magnitude of the flux density of the magnitude at X and Y. Of course, inside the solid it is almost the same, or it is approximately uniform. So I would say approximately equal. Inside the solenoid it is approximately equal. Approximately equal. or you say the field is uniform. So it is approximately equal since inside the solenoid the field is uniform. Then at Y and Z, note that Y is closer to the poles of the solenoid. So the field at Y is going to be stronger than the field at Z. Remember, the magnetic field is always strongest at the poles. One end behaves as if it is a north pole, the other end behaves as if it is a south pole. So the flux density is greater at Y than at Z. I repeat myself, because the coil behaves as if it is a magnet, and for a magnet, the magnetic field strength is stronger closest to the poles. So it means Y is closer to the end. It means the magnetic field is going to be stronger than outside. So it is stronger than Z. So it is greater than Z. Okay. Two long parallel current carrying wires are placed near to each other in a vacuum. Explain why these wires exert a magnetic force on each other. You may draw a label diagram if you wish. Okay, I will draw a label diagram and still I will explain. So if I consider, I'm going to consider two currents into the page. So let's have one current here into the page. I'll use a cross for into the page, and another current here into the page. So remember, by the right hand grip rule, the magnetic field of A and B, the magnetic field of A around B are going to be concentric circles. So I'll draw one concentric circle around. So if I use the right hand grip rule at A, you hold your pen in your right hand and make sure that the sharp end of the pen points towards your page. It means the magnetic field here is clockwise. So at just B, the magnetic field is a tangent which is vertically downwards. Remember, the current is into the page. So now I pull out Fleming's left hand rule. With a magnetic field being downwards, the first finger points downwards. The second finger must point to the page. If the second finger points to the page using Fleming's left hand rule, let me see if I still have my animation here. The second finger is supposed to point downwards. I hope this still works. The first finger is supposed to point downwards with this one has a limitation. That is the problem. Okay, I'll use it to the other side because it has a limitation to its rotation. Okay, so but the force here is going to be towards that direction. Then if I consider the other one, I'll do a magnetic field around A, which goes and crosses into B. So I'm drawing a magnetic field around A, magnetic field line around A, which crosses into B. By the right hand grip rule, with the thumb pointing towards the paper, holding your pen in your right hand, the fingers fold clockwise, so it means the magnetic field is in this direction here. At A, it is just a tangent vertically upwards, so this is the field. It is just upwards, so it means the first finger must point downwards, with the second finger pointing to the page. Let me try back my animation. The first finger must point upwards, with the second finger pointing towards the page. Upwards towards the page. What is wrong with this animation? So the first finger is supposed to point upwards. Upwards. And the second, when I rotate this, just rotate this thumb to, if I rotate the thumb to the right hand side, it is not rotating in the direction I want. But if I rotate the thumb to the right hand side with the first finger pointing vertically upwards, vertically upwards with the thumb pointing to the, with the first finger pointing vertically upwards and the second finger pointing to the page. It is hard to make the second finger pointing to the page, but if the second finger points to the page, the thumb will point to the right hand side. So the force is to that direction. So number one, each of the wires is sitting in the magnetic field of each other. So each of the wires is sitting in the magnetic field of the other, and a current in the wire creates a magnetic field around the wires, and each of the wires is sitting in the magnetic field of the other. So it means by Fleming's left hand rule, there is a force exerted on each of the wires by the other. So to put this in words, I will simply say, so I can label this. This is a current into the page. It is a cross. So these arrows are showing force. This is showing force. Okay, so I can still put this in writing, although the diagram is good. So I can say the current in the wires creates a magnetic field around the wire. That's number one. And each wire sits in the magnetic field created by the other. Each wire sits in the magnetic field created by the other. Each wire sits in the magnetic field created by the other. And by the way, for each wire, the current is perpendicular to the magnetic field. For each wire, the current is perpendicular to the magnetic field. For each wire, the current is perpendicular to the magnetic field due to the other wire. So it experiences a force. So by Fleming's, okay, let me write this in full. Fleming's left hand rule. So by Fleming's left hand rule, each wire experiences a force. Okay, so for example, here the current is into the page, but the field at B caused by A is vertically downwards. So for the current into the page and the field is vertically downwards, it means they are at right angles to each other. And by Fleming's left hand rule, if the first finger points downwards and the second finger points onto your book or onto your paper or onto your page, the thumb must point to the left hand side. And do the same at A. Okay, so that is magnetic fields. Okay, so this is almost still magnetism, but this is electromagnetic induction. And so when you're preparing for an exam, be sure that some chances are high that magnetism and the electromagnetic induction could take 20 marks out of 100. So this is stating Faraday's law. Remember, there are two laws here. There is Faraday's law, which talks about magnitude, and there is Lenz's law, which talks about direction. So for Faraday, The magnitude of the induced EMF is directly proportional to the rate of change of magnetic flux linkage. Magnitude of induced EMF. Magnitude of induced EMF is directly proportional to the rate of change of magnetic flux linkage. If it was Lenz's law, it would be about the direction of the induced EMF being such as to cause effects that oppose the change producing it. So two coils are wound on an ion bar as shown here. Okay, one has a voltage supply, one just have a voltmeter. Coil 1 is connected to the potential difference V1 that gives rise to a magnetic field in the ion bar. Okay, the figure shows the variation with the time t of the magnetic flux density B in the ion bar. Okay, so this is magnetic flux density B. I think this is 0.15 and this is 0.25. Okay. A voltmeter measures the EMF that is induced across coil 2. On the figure, sketch the variation with T of V2 between T equals to 0 and T equals to 4. So first of all, where it is a straight line, the induced EMF is going to be constant because the EMF is directly proportional to the rate. A straight line means a constant rate. So EMF is directly proportional to rate. A straight line means a constant rate. So you notice that the line here is parallel to this line here. So this means they are going to be having the same magnitude. So this is going to be the same magnitude as this, and it is a constant magnitude. But then there's this line here which is going downwards. It has a negative gradient. So I have to compare the magnitudes of the gradients first. These are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 boxes. So 10 divided by 0.15. That is for the gradient for the first part. Gradient 1. Then gradient for the second part is going to be, on the vertical it is still 10 boxes starting from the horizontal axis. Then on the x-axis it is between 0.15 to 0.2, which is 0.5, I think. Let me check again. 0.2 minus 0.15, it is 0.05. Okay, the gradient here will be, I'm saying 10 boxes here, remember. Divide by 0.5 seconds, 10 boxes, 0.15 seconds. I just want a number to compare to see which one is bigger and so on and so forth. So for the first one, 10 divided by 0.15. Okay, so this is 200 over 3. Then for this one, it is, I think this is 200. This is 10 divided by 0.05, which is 200. So the gradient for this part here is going to be 3 times the gradient for the first part. Because when I multiply gradient, so you notice that the gradient 2 is 3 times gradient of 1. So if I say the first part is represented by 3 boxes for the first part. The second part will be represented by 9 boxes. But remember the gradient are in opposite directions because this part is positive. By the way, this is also positive. So this will also be 3 boxes here. And then this part will be negative because the gradient here is negative. So I'll go down 9 steps from the x-axis. 1, 2, 3, 4, 5, 6, 7, 8, 9. So for this part, I'll have something like this. So I'll have a step like that one. So So 0.15, I have 3 boxes. So this is a step, horizontal line there. And the other one is from 0.25, 1, 2, 3, 4, 5. I have another horizontal line here. Because the two lines were parallel, so they have the same magnitude, same gradient. But then between 0.15 and 0.25, we had an opposite magnitude. So this goes down, and it was 3 times. So this goes down to 9 small boxes. Okay, so you can use a ruler to draw a better diagram. But literally, that is how the graph looks like. Okay. Then coil 2 in B is now replaced with a copper ring that rests loosely on top of coil 1. The supply to coil 1 is replaced with a cell and a switch that is initially open, as shown in the figure. Of course, remember the cell provides a constant DC. There's only a change in magnetic field when we close, which again goes back to 0. And then when we open, which again goes back to, when we close, which goes to maximum. And when we open, where it just goes to 0. So in both cases, when it becomes constant, the ring will jump and come back to its normal position. The switch is now closed. As it is closed, the copper ring is observed to jump upwards. Explain why this jump. Okay. Of course, closing is going to create a change in magnetic field from 0 to a certain maximum value. And by Faraday's law, there will be an induced EMF. Okay. So the switch is now closed, so there is a changing current. So changing current in the coil causes a changing magnetic field, which induces an EMF in the ring. So I'll start from that point. Changing current in the coil causes changing magnetic field. So changing current in the coil causes changing magnetic field, which induces an EMF in the ring. So which induces an EMF in the ring. What does the induced EMF do? Of course, the induced EMF creates a current in the ring. And of course, by Faraday's, the induced EMF causes a current in the ring. And by Lenz's law, the induced EMF is going to create, or the current is going to create another magnetic field, which is going to oppose the change causing it, which is like going to create repelling forces. That's why the ring is going to be jumping upwards. So I would say the induced EMF in the ring causes a current in the ring. So there are now going to be two magnetic fields here, one from the coil and another one from the current which is induced in the copper ring. These two magnetic fields are going to cause forces which are going to cause the ring to jump upwards. So the magnetic field due to the induced current in the ring interacts with the coil's field to cause an upward force on the ring. The magnetic field due to induced current in the ring interacts with the coil's field to cause an upward force. So to cause an upward force or upwards force on the ring. So alternatively, we could talk about the induced current in the ring being perpendicular to the coil's magnetic field. And if the induced current in the ring is perpendicular to the coil's magnetic field, still it will cause an upward force because by Lenz's law, let's say the current here is flowing in this direction here. It is flowing in that direction there. So the induced current here in the ring, is going to be perpendicular to the, of course, the magnetic field might be in this direction here. The magnetic field caused by the coil in that direction, so and the current in the ring would be in one of the directions. So if the magnetic field B is perpendicular to the current, then it is still going to cause an upward force, which is going to be caused by Fleming's left-hand rule. So the current and the magnetic field are perpendicular to each other, so this would still cause an upward force. So I would still say, after saying the changing current in the coil causes a changing magnetic field, which induces an EMF in the ring, then I will say from that point, I will say the induced current in the ring is perpendicular to the coil's magnetic field. Is perpendicular to the coil's magnetic field, which causes an upward force on the ring. Which causes an upward force on the ring. So as long as the induced current is perpendicular to the magnetic field of the is perpendicular to the coil's magnetic field, still there will be a force on the ring. Okay. So just with the reason, what would be the effect of repeating the procedure with the terminals of the cell reversed? We are reversing the terminals of the cell. That means the direction of jump will still be upwards. Why? Both the magnetic fields reverse directions at the same time. The one which is inducing reverse direction at the same time with the one which is induced in the what? In the ring. And since both magnetic fields reverse at the same time, it means the force on the ring remains upwards. So I'll simply say both magnetic fields reverse direction. Both magnetic fields reverse direction, so the ring still jumps upwards. The ring will still jump upwards because it will still experience an upward force. The force is just repulsive, Or you could simply say the current in the ring and the coil's fields both reverse, so the ring still jumps upwards. The current in the ring and the coil, and the coil's field, or you can say the current in the ring and the coil's field both reverse at the same time. Reverse, so the ring still jumps upwards. Okay, so if you reverse the terminals so that the current here flows in this direction here, it means the magnetic field in the ring will also reverse, because the magnetic field in around the coil 1 has reversed. The one in the induced current in the ring will also reverse immediately, and that means the force will still remain in the same direction. Okay. Otherwise, if the terminals were to be reversed and the induced current doesn't reverse direction, then it would jump downwards, which is practically not possible. Okay, next is quantum physics. State one piece of experimental evidence for the particulate nature of electromagnetic radiation. Particulate from particle. So these are particulate nature. We have basically two. Number one is photoelectric effect. And number two is Compton effect or Compton scattering. These ones show that electromagnetic radiation is behaving as particles. Then the wave nature. Electromagnetic radiation behaving as waves. This is commonly electron diffraction. The wave nature of matter, that is electron diffraction, not electromagnetic radiation. Electron diffraction. Then you calculate the de Broglie wavelength, lambda of an alpha particle moving at a speed of 6.2 times 10 to the power of 7. So we know that the Broglie wavelength lambda is equal to h divided by the momentum, which is h divided by mv, which is going to be 6.63 times 10 to the power of minus 34, divided by the mass it is an alpha particle whose mass is 4 times u. So that is 4 times 1 u is 1.66 times 10 to the power of minus 27 in kilograms. Then times the speed, which is 6.2 times 10 to the power of 7. So we have 6.63 exponent minus 34 divided by 4 times 1.66 exponent minus 27. I can still divide by 6.2 exponent 7. So I'm getting 1.6 times 10 to the power of minus 15 meters. The speed v of the alpha particle in B Roman 1 is gradually reduced to 0. On the figure sketch, the variation with v of lambda. So we have seen lambda is equal to h divided by mv. So in other words, lambda is directly inversely proportional to v. So that can't be a straight line, it is an exponential curve. Of course, if v tends to 0, lambda tends to infinity, and that means the reverse is also true. As lambda tends to 0, v will be tending to infinity. So I'll just draw a curve which is exponential. Okay, so I should draw a curve which is asymptotic to the axis but not touching any of the axes. Then suggest an explanation for why people are not observed to diffract when they walk through a doorway. Okay, let's first check for diffraction to be observable, the wavelength should be approximately the same as the size of the gap. Let's say the window, the doorway is approximately, let's say 1 meter. Let's say the door is 1 meter. And let's say the mass of a person is, let's say, 80 kilograms for a normal person. Let's check the de Broglie wavelength. Let's say the person is running through the door very fast. Let's say at 10 meters per second. I think that is the fastest um, speed of person on him. I've used the highest speed if someone is just running very fast. So the de Broglie wavelength will be h over mv, which will be 6.63 times 10 to the power of minus 34 divided by 80 divided by, times 10. So this is going to be 6.63 exponent minus 34 divided by 800. So this is going to be 8.3 times 10 to the power of minus 37 meters. So that is going to be the de Broglie wavelength. But remember, the size of the doorway is 1 meter, and the de Broglie wavelength is very small. So the de Broglie wavelength of a person is negligible compared to the width of the doorway. So it is not, diffraction is not going to be observable. For it to be observable, the wavelength must be approximately the same as the size of the gap. So I'll say de Broglie wavelength of a person is negligible. Is negligible compared with the de Broglie wavelength of a person is negligible compared with the width of a doorway. So diffraction is not observable. Okay, so diffraction cannot occur or it cannot be observed because notice the de Broglie wavelength is too small compared to the size of the doorway. For diffraction to be observed, the de Broglie wavelength should be almost the same as the size of the gap. Then astrophysics and cosmology state Hubble's law. Of course, Hubble's law V, the recessional velocity is equal to, V is supposed to be equal to h naught times d. The recessional speed of a galaxy is directly proportional to the distance of the galaxy from the Earth. So V is directly proportional to d. The recessional speed of the galaxy is directly proportional to the distance of the galaxy from the Earth. Because observations are taken from the Earth, that's why we say distance from the Earth. And also, this only applies to distant galaxies, not for any object in our own galaxy. Explain how cosmologists use observations of emission spectra from stars in distant galaxies to determine that the universe is expanding. Of course, the wavelength of these spectral lines must be examined, and then they have to be compared with their known values in the laboratory. If there is a redshift, then it means the galaxies are moving away from the Earth. So I would say the wavelengths of spectral lines The wavelengths, when I say wavelength, that is the plural of spectral lines, are greater actually. They are greater than their known values in the laboratory. So if the wavelength of the spectral lines in light from distant galaxies are greater than their known values in the laboratory, then we can simply say, or astronomers would say, that this redshift shows that distant galaxies are moving away from the Earth. So distant galaxies are moving away from the Earth, hence the universe is expanding. So wavelengths of spectral lines are greater than their known values. And this redshift shows that distant galaxies are moving away from the Earth. And if they are moving away from the Earth, it is only because the universe is expanding. That's how cosmologists use observations of spectra from stars to determine that the universe is expanding. Then explain how Hubble's law and the idea of the expanding universe lead to the Big Bang theory of the origin of the universe. Hubble's law, remember, V is equal to h naught times the rotational speed directly proportional to the distance. And number two, the idea of the expanding. The redshift shows that the galaxies are moving away from each other. So it means the more redshifted, the faster they should be moving away from each other. And thus, and this is actually the Big Bang. If they are moving faster away from each other, if they are farther away, they are moving faster and they are more redshifted, then it means they must have started from the same singular point. That is actually the idea of the Big Bang. So we can say all parts of the universe, all parts of the universe are moving away from each other. That is according to the idea of the expanding universe. All parts of the universe are moving away from each other. So if all parts are moving away from each other, it means the more distant an object is, the faster it must be moving. So we can say more distant objects more distant objects are moving away faster. More distant objects are moving away faster, so matter must have started. If more distant objects are moving away faster or more redshifted, so matter must have been close together in a very dense singular point in the past. So matter must have been close together in a very dense singular point in the past. Because remember, the Big Bang theory predicts that the universe started as a small, dense, singular point, which tremendously started expanding And during the expansion, the density started decreasing and the temperature also started decreasing. And then, of course, the expansion is still going on. So, if we can, if we consider all the parts of the universe moving away from each other, and with the more distant objects moving faster, then we can predict that if we were to trace back where everything started from, then matter must have been close together in a very dense singular point in the past. That is the idea of the Big Bang. Okay, so that is cosmology and astrophysics. Then next and last is, I think this is the last. It is going to be, I think this is nuclear physics. State what is meant by radioactivity. Of course, radioactivity, this is spontaneous and random. So this is going to be the spontaneous and random disintegration of an unstable nucleus. Of course, this is through the emission of ionizing radiations, such as alpha, beta, and gamma. So that is radioactivity. Remember, radioactivity. Remember, spontaneous means not affected by external factors such as temperature and pressure, and random means cannot be predicted. Okay, a radioactive sample consists of an isotope X of half-life T. So the half-life is capital T, that decays to form a stable product. Only X and the stable product are present. Okay. At time t equals to 0, the sample has an activity A naught and contains N naught nuclei of X. So in other words, activity is going to be lambda times N naught. N naught is equal to lambda times N naught. On the figure, sketch the variation with T of the number N of nuclei of X present in the sample. Your line should extend from t equals to 0 to t equals 3t. Of course, at t equals to 0, n equals to n naught. So for t equals to 0, n is n naught. So we start from this point here. Then at t equals to half-life, that is capital T, n is equal to a half of the original, because half-life is the time taken for the number of nuclei present reduced to half. So this will be n naught over 2, which is 0.5. Then at t equals to, let's say, twice half-life, n will be n naught divided by 2 again, so it becomes n naught over 2 divided by 2, which is n naught over 4. So this is 0.25 n naught. Then we can check at t equals 3 half-lives. N will be equal to n naught over 4 divided by 2 again, which is n naught over 8, which is, I think, 0.125 n naught. So what is 0.125? Let me check with the scale. 0.25 divided by 10. So 0.125 divided by the scale. So those are 5 boxes. Are they 5 boxes? 0.125. Yeah, I think there are 5 boxes. So it is here. 1, 2, 3, 4, 5. Okay, so this is going to be a smooth curve. Let me try to increase the thickness. So you draw a smooth curve with a pencil from the top. Okay, so that is going to be the curve. Then on the figure 10.2, sketch the variation with n of the activity A of the sample for values of n between n equals to 0 and n equals to n naught. Remember, activity is directly proportional, or activity is equal to lambda times n. So n naught equals to n naught. So this is going to be activity is directly proportional to n, which is going to be a straight line through the origin. When n is 0, the activity is, of course, 0. So this is going to be a straight line through the origin. So graph of activity against n is going to be a straight line through the origin. Okay, so that is going to be a straight line through the origin. Then state the name of the quantity represented by the gradient of your line in figure 10.1. The line in figure 10.1, so I have the gradient is going to be change in n divided by change in t, that is the gradient. Of course, this is going to be activity. Activity is the number of nuclei decaying per unit time, that is activity. So the gradient is going to represent activity. So this is going to be activity because it's change in n on the vertical over change in t. Number of nuclei decaying per unit time, that is activity, or the probability of decay, that is activity. Then state the name of the quantity represented by the gradient of your line in 10.2. So remember, this is activity is equal to lambda times n. When you compare with y equals to mx plus c, you notice that if I have activity on the y-axis and n on the x-axis, the gradient is lambda, which is the decay constant. So this is going to be decay constant. Then for the sample in B, calculate the fraction n over n naught at time t equals to 1.7. So we know the general equation n equals to n naught e power negative lambda t. And of course, we also know that half-life, or the decay constant A, lambda is equal to ln of 2 divided by t a half. Okay, so n divided by n naught is going to be equal to e power negative, where there is decay constant, I'll put ln of 2 over t a half, and half-life was t, by the way. This was ln of 2 divided by capital T, because half-life was capital T. Then I multiply this by small letter t. But remember, t is 1.7, so the fraction n over n naught is going to be equal to e power negative, where there is small t, I'll put 1.70 capital T ln of 2 divided by capital T, and capital T cancels out. So this becomes e power minus 1.7 ln of 2. I'll press my calculator, shift e, power negative 1.7 ln of 2. So this is giving me 0.3077, so it is 0.31. So this is 0.31. Okay, I think that marks the end of this paper. I don't know whether there is another question. Okay, so that marks the end of the paper. I hope you have learned something from this. If there is any question, you can always raise your question. Until next time, bye bye. Love you.